Inorganic Chemistry, Round 1, Part 6. The iron deficiency of iron 2 oxide. Iron 2 oxide or ferrous oxide is the inorganic compound with the formula FeO. Its mineral form is known as woostite. Iron 2 oxide adopts the cubic rock salt structure where iron atoms are octahedrally coordinated by oxygen atoms, and the oxygen atoms are octahedrally coordinated by iron atoms. Iron 2 oxide also refers to a family of related non-stoichiometric compounds which are typically iron deficient with compositions ranging from Fe 0.840 to Fe 0.950. The non-stoichiometry occurs because of the ease of oxidation of Fe2 to Fe3, effectively replacing a small portion of Fe2 with 2/3 their number of Fe3, which take up tetrahedral positions in the closed-packed oxide lattice. The anion excess nature of uranium-4 oxide. Uranium dioxide or uranium-4 oxide, UO2, also known as urania or Uranus oxide, is an oxide of uranium. The solid is isostructural, has the same structure as fluorite, calcium fluoride, where each uranium is surrounded by 8 oxygen nearest neighbors in a cubic arrangement. In addition, the dioxides of cerium, thorium, plutonium, and neptunium have the same structures. No other elemental dioxides have the fluorite structure. Upon melting, the measured average UO coordination reduces from 8 in the crystalline solid, UO8 cubes, to uranium dioxide, UO2. In this structure, the oxygen anions are bonded to only 4 cations, U4+. Oxides with this structure are well known for the ease with which oxygen vacancies can be formed. At room temperature, uranium dioxide assumes the fluorite structure with both uranium and oxygen atoms vibrating isotropically about their equilibrium positions. At higher temperatures, greater than 400 degrees Kelvin, this model must be modified to account for the anharmic anisotropic contribution of the oxygen atoms to the Bragg intensities. Up to 1300 degrees Kelvin, the uranium atoms continue to vibrate isotropically. On oxidation of UO2 to UO2 plus X, defect clusters are formed in the oxygen sublattice. At X equals 0.12, diffraction studies indicate that the configuration of the cluster is 2-2-2, i.e. consisting of 2 vacant oxygen sites, 2 interstitial oxygens displaced away from the cubic coordinated interstitial site, and 2 oxygens displaced. The uranium sublattice is not disturbed by the rearrangement of atoms in the oxygen sublattice. At the limiting composition of UO2.25 or U409, the oxygen clusters linked together in an ordered superlattice structure exist in hyperstoichiometric form, UO2 plus X. Those excess oxygen atoms occur at interstitial defects, and these defects are not random but rather partially ordered. The widely accepted model to date, the Willis cluster based on neutron diffraction, cannot be reconciled with the first principles of molecular dynamics simulations present here. The Willis cluster is a fair representation of the numerical ratio of different interstitial oxygen atoms. However, the model does not represent the actual local configuration. The simulations show that the average structure of UO2 plus X involves a combination of defect structures including split di-interstitial, mono-interstitial, and Willis cluster, and the latter is a transition state that provides for the fast diffusion of the defect cluster. The results provide new insights on differentiating the average structure from the local configuration of defects in a solid and the transport properties of UO2 plus X. The activity of any pure substance in its standard state is defined to be unity. The larger the value of Ka, the stronger the acid. The smaller the value of pKa, the stronger the acid. The larger the value of Kb, the stronger the base. The smaller the value of pKb, the stronger the base. The IUPAC definition of an oxo acid is a compound which contains oxygen, at least one other element, at least one hydrogen bound to the oxygen, and which produces a conjugate base by proton loss. Suggest why beryllium 2+ has a higher affinity for H2O molecules than magnesium 2+. Beryllium 2+ has a smaller ionic radius and a higher charge density compared to magnesium, Mg2+, which affects its ability to form stable complexes with water molecules. Tabulated values of solubilities of ionic salts refer to the maximum amount of solid that will dissolve in a given mass of water. Solubilities may also be expressed in concentrations, molalities, or mole fractions. If a salt Mx is added to an aqueous solution containing the solute My, the ion M N+ is compared to both salts. The presence of the dissolved M N+ ion suppresses the dissolution of Mx compared to that in pure water. This is the common ion effect. Gravimetric analysis is a quantitative technique in which the material under study is isolated as a precipitate. The word ligand is derived from the Latin verb ligare, meaning to bind. In a coordination complex, a central atom or ion is coordinated by one or more molecules or ions, ligands, which act as Lewis bases, forming coordinate bonds with the central atom or ion. The latter acts as a Lewis acid. Atoms in the ligands that are directly bonded to the central atom or ion are donor atoms. In a complex, a line is strictly used to denote the interactions between anionic ligand and the acceptor. An arrow is strictly used to show the donation of an electron pair from a neutral ligand to an acceptor. When a Lewis base donates a pair of electrons to a Lewis acid, a coordinate bond is formed and the resulting species is an adduct. The centered dot in, for example, H3BTHF indicates the formation of an adduct. Solvent extraction involves extraction of a substance using a suitable solvent. In the two-phase solvent system, the solute is extracted from one solvent into another, the extracting solvent being chosen so that impurities remain in the original solvent. Polydente ligands form a more stable complex than monodente ones. The density of a ligand is the number of donor atoms through which the ligand coordinates to a metal atom or ion. The density of a ligand is designated by the prefix K, kappa. Coordination of a polydente ligand to an ion leads to the formation of a chelate ring. The word chelate is derived from the Greek word for a crab's claw. For a given metal ion, the thermodynamic stability of a chelated complex involving bidente or polydente ligands is greater than that of a complex containing a corresponding number of comparable monodente ligands. This is called the chelate effect. The stabilities of complexes of the non-d block metal ions of a given charge normally decreases with increasing cation size. The size of the ion is in a crystallographic sense. Thus, for a complex with a given ligand L, the order of stability is calcium 2+, selenium 2+, barium 2+. Similar behavior is found for lanthanide M3+ ions. For ions of similar size, the stability of a complex with a specified ligand increases substantially as the ionic charge increases. E.g., Li+ less than Mg2+ less than aluminum 3+.